In physics, understanding rotational motion is crucial, and the moment of inertia plays a pivotal role. Imagine a spinning top or a figure skater turning. The moment of inertia, denoted as I, quantifies resistance to changes in rotational motion. Think of it as the rotational counterpart of mass. A higher moment of inertia means it's harder to start or stop spinning. It depends on the object's mass and its distribution relative to the axis. Weights farther from the axis increase the moment of inertia. Closely related to the moment of inertia is the concept of the radius of gyration, denoted as k. Imagine you could concentrate all of an object's mass into a single point at a certain distance from the axis of rotation. The radius of gyration is that distance, the distance at which, if all the mass were concentrated, the object would have the same moment of inertia as it does with its actual mass distribution. Mathematically, the relationship between the moment of inertia, I, mass, m, and radius of gyration, k, is expressed as I equals mk2. The radius of gyration helps us understand how the mass distribution affects an object's rotational properties. Now, let's dive into some common geometrical shapes and their moments of inertia. These are essential for NEET preparation. I in 1/12 times m times L squared, where m is the mass and L is the length of the rod. I.e. 1/3 times m times L squared. I.e. 1/2 times m times r squared, where r is the radius of the cylinder or disk. I.e. m times r squared. I.e. 2/5 times m times r squared. I equals 2/3 times m times r squared. Section 4. Mastering parallel and perpendicular axis theorems. Calculating the moment of inertia for complex shapes can be simplified using the parallel and perpendicular axis theorems. Parallel axis theorem. If you know the moment of inertia of an object about its center of mass, I chem, you can find it about a parallel axis using I equals ICM plus MD squared. Perpendicular axis theorem. For planar objects, if you know Ix and Iy, you can find Iz using Iz equals Ix plus Iy. These theorems help break down complex shapes and calculate their moments of inertia. Section 5. Real-world applications of moment of inertia. The concept of the moment of inertia extends beyond textbooks and finds applications in various real-world scenarios. Engineering design. Engineers use the moment of inertia to design structures and machines that can withstand rotational forces. For example, designing flywheels for engines or calculating the stability of rotating machinery. Sports. In sports like figure skating, diving, and gymnastics, athletes manipulate their body positions to alter their moments of inertia, affecting their rotational speed. Astronomy. Astronomers use the moment of inertia to study the rotation of planets and stars, helping us understand their formation and evolution. Robotics. Robotics engineers consider the moment of inertia when designing robots that need to move and rotate precisely, such as robotic arms used in manufacturing. Section 6. Putting knowledge to the test. NEET questions and memory aids. To succeed in NEET, practice is key. Here are some previous year's questions related to the moment of inertia. 1. Insert a previous year's NEET question here. 2. Insert another previous year's NEET question here. Memory aids. Remember the basic formula. I equals m squared. It tells us that the moment of inertia is about the sum of mass particles multiplied by their distances squared from the axis of rotation. Visualize the shapes. When dealing with different shapes, try to visualize how the mass is distributed and how that affects its resistance to rotation. Practice, practice, practice. Solve as many problems as you can to solidify your understanding of the moment of inertia and its applications. By grasping the concept of the moment of inertia, mastering the formulas, and practicing diligently, you'll be well prepared to tackle any NEET question on this topic. Good luck.